Uh, as far as I recall, I think this is where we were yesterday. We were looking at the entities that we were interested in and how intensity depends on the direction, which is defined by two sky coordinates, what color it has, that means how does it vary as a function of frequency, how, how does it change with time, and if we are lucky, we also would like to know its polarization state. So is my okay, the Zoom. All right, let me. All right, it's not allowing me to now to go to Zoom to set my video, but that's not probably important. Okay. All right. So the important part is that while we would like to have the widest span and finest resolution in each one of these, including the intensity, which when it relates to the intensity, we normally refer to the ratio of the span to the resolution as dynamic range. That means what is the highest intensity we can measure and with what fineness we can make the measurement. So the important part is that not while we would like to have the widest span and finest resolution, not all of it can be specified mutually independently. There is a specific constraint coming from Heisenberg's uncertainty principle, which stops us from being greedy, as I said last time. And we also looked at some of the pairs that will have these constraints coming along. And so you can, we will talk about Fourier transform separately, but in any Fourier pair, the Heisenberg uncertainty principle holds good. You will find the span in one defines the resolution in the other domain and vice versa. So you will find that once you choose something, the other domain parameters are will have the restriction even in the best case, the limiting case of equality of the Heisenberg uncertainty relation. So as you know, or we will look at it in more detail, you will find if the width of some description in one domain is something, the corresponding description in the other domain will have a width which is inverse of the width in one domain. And you will we will come across this in variety of ways and variety of pairs of parameters which are Fourier related. Okay, so even for a single photon case, even without appealing to the classical description, we can begin to appreciate that there are certain unavoidables and relevant aspects of the uncertainty principle that will limit the fineness with which we can do things if we have certain fineness that is expected or imposed in one of the domains. For example, here, if we collect photons across the size of the aperture, which is, let's say, D, we are allowing the uncertainty of where it actually fell within this aperture. And this gains us the ability to pinpoint the direction from which essentially the momentum component along X. So for a given wavelength and a photon energy, you can write down uh, the corresponding momentum, which is h nu by c. You can take its component along X, and delta X is the uncertainty you have allowed in the X direction, and the component of the momentum in X will be the photon momentum times sine of theta. And if you say there's no uncertainty in the wavelength, that will translate to uncertainty in sine theta. And for small angles, sine theta can be assumed to be comparable to theta. And then you can get a constraint on the delta theta, really speaking, which you can work out the diffraction formula from simple considerations of uncertainty principle application. Similarly, along the path of the photon, you can take a section and say, if I say the photon is within this position range along the path of the photon, if I allow that uncertainty, can I specify the frequency more accurately? You can see that this argument will allow you to derive the uncertainty principle associated with the or by applying the uncertainty principle in energy and time, you will be able to get the description of how fast a filter with certain bandwidth can respond, or how much detail you can see when your signal has gone through some filter. The variety of context this relation will come in. All right. So with this understanding, which we will go into greater detail,
Hello, Desh.
Desh, I think you've lost your voice.
Hello, Desh.
Hi, sorry about this. Desh is having problems with his laptop. We're not able to actually get in touch with him. I'm sure he's trying to sort things out. Meanwhile, if Desh can't come back in a few minutes, Prakash, who is scheduled to speak to you all about the project after Desh, will start off soon, and then we will schedule Desh's talk in Prakash's slot. So we'll just see how it goes in the next few minutes. Either Desh or Prakash will be with you. Sorry about this. What will happen now? Because Desh is sharing, so I should. I'll talk to Jamil. Second. Hi, Jamil. Jamil, actually, I mean, this Prakash says he could speak, but I was not able to get through to Prakash right now again. So, but the thing is that Desh is already sharing his screen. So can you? So how will that work? If I put multiple participants can share simultaneously, then I don't know how that is going to happen. Okay, you can take him off. Okay,
Hello, can everybody hear me?
Yes, sir.
Yes, sir.
Okay, great. Is Desh again trying to join? Desh,
uh,
you hear us? We don't hear you yet.
yeah. I'm trying to call him as well, but he's not picking up the phone because he's trying to busy doing things. I'm not sure he's able to hear us either. Anyway, he seems to have put his screen on full screen mode.
Okay, let me get things in order.
I think Prakash, just be ready. Let's just wait for half a minute.
Sure. And I close this.
Hi, Desh.
Okay, maybe I can start out a bit and we'll see if Desh joins, whether he wants to continue or do it later. Is that all right, Saikya? Okay, he might be on a call. We'll wait.
Hi, Prakash.
Yeah, go on, Saikya.
Yeah, you're audible. I just spoke with Desh. You can go ahead, actually. Why don't you go ahead and then Desh will catch up after you.
Okay, sounds good. Just a minute. Okay. Actually, the video is sort of blocking my screen, so I'll stop for now. Okay, hello everyone. Um, so we're going to be slightly ahead of schedule on this presentation, but I hope that's okay. By this time, I'm assuming you would have looked at the folders, the contents of the folders, and we have put these worksheets and a Python notebook, which has some ORT data algorithms to say how you would go about analyzing ORT data. I thought I'll give a brief introduction to these worksheets and the data analysis, which will give sort of a broader context for you to understand what we are trying to do here. Because the worksheets themselves may be a bit short on the introduction part. So the module one is going to be on what I've titled as antenna feed electromagnetics. I'll start with the motivation of why I thought about presenting this as a worksheet. So the initial motivation was for me to understand how to fundamentally understand how an antenna works. That is how it detects electromagnetic radiation. So you must have got the idea by now that a radio telescope, it's not exactly like the other cameras that we use to detect photons in the optical or even in the high energy. It works slightly differently. And although everybody has some idea of how it works, a general uh, picture they have in their mind, where a changing electric field is what is incident on a piece of metal, a wire, let's say, and it moves the free electrons and that produces current. That's the general description, and it's accurate enough or good enough qualitatively. Here is a GIF that is on Wikipedia that illustrates this very well for a short dipole. What you see is here is a short dipole where the currents are flowing. You can see the negatives and positives alternating as the electromagnetic wave propagates and the electric field pushes the electrons one way or the other, depending on the vector, the electric vector. And there is a resistor that connects the two elements of the dipole, and that completes the circuit. Okay, this is good, but this particular qualitative way of looking at things does not really help one to design a simple antenna, for instance. So one needs to go slightly deeper, and if one wants to think about how to actually go about building an antenna with simple components. Now, this is the motivation part where I was thinking, let's say I do have to design an antenna. How would I go about it? Like what all are the things that I would need to learn about to go about doing that? I mean, a theory can take you quite far, even though it's no substitution for actually tinkering with stuff and doing it hands-on. The other motivation is, I mean, I was thinking how, for instance, it's quite a bit popular nowadays in pop culture media. If you see, there's always a post-apocalyptic world. I was wondering if we were in such a world, like how would you go about improvising an antenna? I mean, you would have to know it in quite a bit of detail for you to improvise it and make an actual functioning antenna for your purposes. So these were the general motivation. But I mean, I'm sorry to say I don't have the complete answer yet, but I have a few steps like we can take. We can see how deep we can go with some of the basic principles that we know and the mathematical techniques we can apply and see. So I tried to come up with a few set of prerequisites for it. I know, I mean, I'm not too aware of uh, the different syllabus in different universities all around the country. Um, I mean, most of you are from a bachelor's degree, but I'm assuming you have done some amount of electrodynamics. Uh, so these are sort of what is required in electrodynamics. It would be good if you, I mean, it would really make sense only if you know Maxwell's equations well, the wave solution, the scalar and vector potential description of how to describe electric and magnetic fields, and the retarded solutions. These are some of the prerequisites. Let me see. Hold on. Okay. As you go along with, I mean, I would like to know if, okay, let me quickly check something. Okay, I want to get a feel of how many of you are actually familiar with these things. Like you have done it at least once in your course. You may not be very proficient in it, but you can get back to it. You can understand things. Can I see a quick raise of hands from everybody who understands these things? You can go next to your name in the participant list, or there should be an icon which says raise hand. So it will give me a rough idea of whether, okay, that's great. I'll ask a few questions in between like this, so make sure you know how to raise your hand. I see a fair number, but not everyone. I'll tell you how to deal with that. I mean, partially you can still go through some of these worksheets, and you know, you can always get help from your mentor and your fellow group mates. Okay, you can put your hands down now. The other thing you would need is, let's get back to the presentation, is basic circuit theory. Hold on. Right. Basic circuit theory, like knowing how to calculate electric power, knowing what the circuit elements are, knowing what impedance is, like uh, the combination of resistance and reactance. You know these things, or even for this case, at least for the circuit theory part, you can just look at basic definitions on Wikipedia or some online resource, and that should be good enough. We won't go too much into detail with these things. And about black body radiation, thermodynamic equilibrium, I'm assuming all of you would have some idea about, like, have encountered it in your coursework or even in lectures like these, like it was discussed even in the past 2 days. There might be other prerequisites I haven't considered really, but what I would like is eventually you guys to give me feedback as to uh, what would be nice little modules to add that would help bridge the gap between what you already know and to solve the worksheets that I'm about to show you. Okay, so we'll jump right into it. We'll look at the antenna feed. Now, antenna feed is essentially the set of elements in a telescope which converts which acts based on the electric field that is incident on it and produces a current. So we'll go with the most simplest setup, which is a dipole antenna. You have two linear elements. If you see, there's a schematic that is drawn on the right side. There are two uh, two sort of elements, one oriented up and one oriented down, and they're connected through a electrical load. And this is pretty much it. I mean, this is the simplest form. And if you look at an actual picture of a dipole antenna feed, you'll see that it looks pretty much like the schematic that I've shown. There's not much more to it. So first thing you would work over there is trying to see if for a given electric field that is incident on an antenna feed, what is the current excitation that happens in the circuit. Now, this seemed like a simple, basic question to ask, and that is why I started looking for a solution. But it's not an easy solution to come by. Like, it's searching online, I had to actually go to a lot of engineering books where they talk in detail about antenna theory for me to get close to a solution. It's still not complete, as you'll see. So what we are trying to do is solve the simplest problem, and a plane wave is incident on this dipole. And because it's a plane wave from a very distant source, the electric field that you can measure at all the points on this linear dipole will be the same at a particular instant of time. And we'll see what is the current that will be generated due to this. Now, this is called the antenna boundary value problem, where you solve the Maxwell's equations within the antenna element, and you apply the boundary conditions of the antenna and get a solution. It sounds straightforward. So I'll just go over the basic steps. I mean, eventually, when the whole point of those worksheets is that you'll have more time to work on it and probably get a better idea of what exactly is going on rather than listening to me speak about the overview. But I'll just give briefly describe the steps that you will take to get to the equation that governs the solution, not the solution itself. Okay, the first part is to realize that it's a kind of metallic sensing element, which means if you choose a good conductor, the electric fields of the surface need to be canceled. So as the for an incident electric field, there would be currents that would produce an electric field to cancel the incident electric field. Now, what that means is we have an electric field at the surface. We'll know that because we have an assumed form of the incident radiation. And from that, we'll use these vector potentials. I mean, again, if you have a background, that's great. Otherwise, the worksheets, what it would do is give you the relations as is. You can assume that to be a given. You can, if you have time, you can go back and see how they are derived, or you can take it for granted for now and then apply it and get to the solution. So essentially, you can apply something called a Lorentz gauge, which exploits the freedom that we have in defining potentials for the electric and magnetic fields. And this allows us to express any electric field in terms of vector potentials alone. So what we'll have is a differential equation of the vector potential, which we'll solve. And then there comes the solution of the inhomogeneous wave equation for Maxwell's equations, which connects the vector potential to currents. That is the expression over here. Many of you who raised the hand uh, about satisfying the prerequisite would immediately recognize it. And once you equate these two, the vector potential that you've obtained from the incident electric field and the vector potential due to or this general wave equation solution, you'll have an integral equation that you need to solve to get the current in the antenna. I mean, this is how far the worksheet will take you. To actually solve it and apply the boundary condition, it turns out to be a lot more complicated. You'll have to convert these into algebraic equations and get an approximate solution at best. Now, this is something in the next session I'll try to go over a bit, but you're not expected to actually find a solution. I mean, if you are really adventurous, which you should be, maybe later after the winter school is over, I'll give you the references you can go about on a weekend, sit and try to solve this. It should be worthwhile. Okay. Yeah, so the general suggestions, I mean, this is just the first section. This is the hardest part. So if you did not understand all the stuff I said in the previous slide, do not worry too much about it. The rest of the worksheets that we're going to work on are not nearly this difficult. It's much more straightforward. And it does not require you to know a lot of this detailed electromagnetics. Okay, but in any case, I've tried to design the worksheet so that either you know the background so that you're convinced of a particular expression that is given that I've said just take for granted, or you just trust it and you take it granted for now and go through the derivations. Or there's a compromise where you go through the derivation and later you go back at some point. I mean, in the future, like after the school, you go back and try to work out the results that you took for granted, derive them again. Okay, so we have gotten over the hard part actually. Now hopefully it would be a lot more accessible, whatever I'm going to explain. Now, so I've sort of explained you right now what I wanted to just remember is that what we have just done is essentially find out the equation which defines what current will be produced for an incident electromagnetic field. Now, we saw the antenna feed. It has these sensing elements. Now we know what current is generated. Not exactly what current is generated, but we know how to get to it. Now, once the current is generated, what happens in an antenna is because the currents are varying with time, the charges are getting accelerated. The currents themselves will radiate back into space, which leads to something called radiation resistance. This happens for both receiving and transmitting antennas. Transmitting antennas will have a voltage oscillator, which will move the charges in a feed, and this will radiate. Um, and the receiving antennas, essentially, the incident electric fields will produce a current that causes acceleration of charges, and the acceleration of charges again lead to radiation. That is radiation resistance. Now we are back to the simple schematic. And in general, if you see this in terms of a circuit, the antenna element, the dipole, will have resistance both loss resistance and radiation resistance, and a bit of reactance in general. But it so happens that, I mean, the loss resistance is something due to, the material itself, and this will be something that depends on how it's designed, and it will stay constant once the design is done. Now, we'll assume for most cases that it's lossless. We have some sort of material where the loss is so minimal we can ignore it. The loss resistance, that is just the opposition in the material to motion of electrons. And if you choose short enough dipoles, it so happens that the reactance itself can be neglected. It will be a purely resistive antenna. That is, when I say short dipoles, what I mean is the length of the linear antenna that we have is smaller than or much smaller than the wavelength we are interested in measuring. So how does one go about calculating radiation resistance of an antenna? We have to first calculate the energy loss due to acceleration of these charges. I mean, it's fairly as simple as that. We know that accelerated charges radiate, and we have to do it for a bunch of charges because we know the current that is there. So the step one would be to determine the transverse electric field due to the current distribution that we have assumed. Now, I told you how to go about calculating the actual currents. It so happens for many applications or trying to understand qualitatively what's happening, we can always make these approximations that are good enough for our purposes. For getting to these expressions, for understanding the concepts, may not be for actually designing an actual antenna, but it so happens a good approximation for a short dipole where the wavelength of interest is larger than the linear extent of the antenna. It can be either approximated by a cosinusoid, where it goes to zero at the edges and maximum towards the center. Or you can even have, for very short dipoles, almost a linear distribution, where it again goes to zero at the edges and its maximum at the center. This is, for instance, one of the expressions where h is the total size and h by 2 is the size of each element. And you can start with a current distribution, assume a current distribution of this sort. And then you have, you know, okay, most of you would know what is the electric field that is generated, transverse electric field generated by an accelerating charge particle, a single charge particle. All you have to do is generalize this for the for the current distribution that we have. If you don't know some of these expressions, it is already given. So all you would have to do is take some of the mathematical steps, like integrating or differentiating and getting to the solution. Hopefully it does still is useful in some way to the people who are not familiar with many of the prerequisites. It's I mean, it's sort of experimental pedagogical technique. We'll see how it pans out. Now, the next thing we'll do now, what we have is we have the electric field due to the current distribution now. Now, from there, we can calculate the Poynting flux due to the propagating electric field. The Poynting vector, as defined here, gives the power uh, that is being emitted due to accelerating charge particle or any distribution that is radiating. And one can take a time average of it, and one gets the power emitted or time average power emitted, because uh, it's a cyclical uh, change in current. That's why we are doing this time averaging. And finally, all we have to do is we have the total power that is being emitted, and what we can do in terms of circuit, we can define a radiation resistance. We can calculate the I square R sort of loss due to a resistance. You have to just equate these two. Once we equate it, we'll get the radiation resistance. Now, what we have, so we have two elements that we have taken care of. In the feed, we have the current distribution, and now we know what sort of resistance it has. The reactance is again somewhat involved calculation if one needs to take reactance into account in the antenna. But we can always make this assumption that we are working in a limit where only the resistance dominates and the reactance is not that important. Now, the third and final part of that first worksheet would be how to extract maximum power out of the electrical load that we have we have in the antenna feed. So again, you see the schematic over here. We have this dipole. We know how what current is, or we sort of know what current is going to be generated. What is the radiation resistance that piece of element has, and the power, or there is a load impedance. The load that we connect is sort of our design, and we know what load is going to be connected over there and what impedance it will have. Now this can be converted to a equivalent electrical circuit. I think there's something called the Thevenin's theorem, which allows you to do that. So what you see on the left, the schematic of the dipole feed, while it's generating its current and has this potential difference across the load impedance, it is exactly equal electrically to the equivalent circuit that we have on the right. We have ZA as the antenna impedance, which has a resistance part and a reactance part. The voltage VA is essentially comes from the electric field that is generated, which moves the electrons there. The current is what we saw, IA, and we have this load impedance. And all you have to do is solve this. So first you'll have to write down the power that is received by the load. That is where we are making the measurements and receiving power. Then what we'll do is we'll expand the impedances. We'll assume we know reactance values and resistance values, so we can write any impedance in terms of reactance plus an imaginary part of reactance, resistance plus imaginary reactance. And it will essentially be a algebraic equation where you have to try to maximize the power output. So this will give you conditions on what sort of load impedance you can choose so that you can get maximum power output. This would pretty much require just some calculus of variations, nothing more than that. So this is supposed to give still a very rough idea of how exactly radiation that is incident on an antenna feed gets converted to current. What are the circuit elements we need to consider for us to get power out of it, and how to maximize that power. Hope that is clear. Okay, that's pretty much the summary. So I'll still go over it again just once more. In summary, what we have done is we have sort of, eventually when you go through the worksheets, you would have gotten to the equation that governs the current excitation in an antenna. You would have found out how to calculate radiation resistance for a given electrical current, right? And then how to do impedance matching. That is the technique that's what it's called for maximum power transfer to the electric load. Okay, what I'll do is I'll give you a few minutes in case you want to ask any questions about this before we move on to the next worksheet, which is radiometer characteristics. Or you can take a break. I mean, if I don't want to go on and on. You can take a 3 minutes break, anybody who wants to. Desh, are you back?
Yes.
Okay.
Yeah.
Would you like to add anything? I mean,
yeah, I had just 2 comments on the
sure.
material in your worksheet number 1. One is referring to the last bit that you just mentioned, how to choose the load resistance or load impedance to maximize the power. And so when you actually write an expression of the voltage division or the current going through the load, and assume the antenna as a voltage source, you can show in just few steps that maximization of power will occur into the load impedance when the load impedance is complex conjugate of the antenna impedance.
I mean, yeah, that actually they figure it out when they do the worksheet.
Oh, I see. That's the part of the worksheet.
That's what they'll figure it out.
Okay. The second comment I have is
Sure.
a little opposite to what was stated for a short dipole. The resonant dipole with lambda by 2 length is the one that is purely resistive.
Okay.
The short dipole can be thought of as the one that gives pure resistive impedance, but parts of it are missing, like the ends, right, which you have cut off to make a short dipole. And that can be imagined to be adding to extra capacitance on top of what you would have as a pure resistive impedance when you have a resonant dipole of half wavelength. And you will have, so when you use any element which is linear element which is smaller than lambda by 2, you will have unavoidable capacitive part to the impedance of the antenna.
Okay.
Becomes a challenge to compensate for it in practice.
I see. Okay, I'll try to make those say that in the worksheet so that it's clear and there's no confusion.
And the radiation resistance in general would scale with the length of the dipole in general. Okay, so when you derive your expressions, you should get that dependence if L is kept as a variable.
Yeah, that's how it is done. Okay,
all right, thanks.
Before we start, any other questions that anybody has? Or Desh, do you want to continue your talk? I can.
No,
just to later.
In fact, I think this was a blessing in disguise. I was actually talking about the antenna and aspects relating to the radiation, radiation pattern, and so on. I don't know where exactly I got cut off, but that's the part that I would have liked to digress into, which you have perfectly done through your first worksheet description.
Okay. Yeah, I mean, these are supposed to just complement your lecture.
No, but the timing of it was also perfect.
Okay, that's good. But would you like to continue? And I can take over this.
Yeah, I can probably do that if it's okay. If it's not too disruptive for the audience.
Yeah, I think it should be fine.
Is that okay, Sakya?
Yeah, that's fine. Whatever works for the two of you, that's perfectly fine. Yeah.
Okay.
So Prakash, you'll have to probably stop screen sharing so that Desh can take over.
Yeah.
Okay. So let me get. Share the screen.
So should we take like a 5 minutes break for the?
Yeah, we can do that.
Yeah, you can.
They might even have some questions on the part that you said.
Oh yeah.
That can deal with that.
Yeah. Do you guys have any questions?
I had a question. One question. Can you again explain how do you characterize whether an antenna is like purely resistive or reactive based on the wavelength it is tuned? I didn't get that clearly.
Desh, could you answer that?
Yeah. So what is the question? How do you decide whether it's resistive or
reactive?
Okay. So essentially, the recipe that Prakash outlined amounts to seeing how the power is radiated, and then you equate that to an equivalent circuit where the radiated power is modeled as something that is lost through an impedance load. And then you work backwards to find out the impedance. And the impedance has an imaginary part. That's the reactance that your antenna would have.
Okay, but what's its wavelength dependence? I mean, for a lambda by 2, you said it's will be purely
Yeah, it turns out that for lambda by 2, you get purely resistive antenna impedance. For longer length, you will get more inductive part, okay, as you can imagine, because you're adding extra length beyond the for a shorter dipole than the lambda by 2 at that wavelength, you will see, of course, all these numbers are wavelength dependent, okay. So you will find that when you have a short dipole, you can imagine that to be the half wave dipole, but with parts missing, which are now the gap in space. And you can imagine as if there was a capacitor there, right?
Yeah, right.
With the air as a dielectric. And so you will find it has, it leads to more capacitive load when you have it slightly longer than the half wavelength. It will amount to, in addition to the resistive part, you will also have an inductive part.
Okay.
But because it all depends on the precise current distribution that you will assume, that you set up on the piece of metal that you have, there is no one immediate answer once you give some shape and size of the piece of metal. You will have to actually work it out and taking into account contributions that are made by every piece of it.
Thanks.
Of course, there are detailed, the simulation softwares which will help you to do that. If you give the shape and size of the antenna, then it will simulate as if you're feeding the signal into it in the radiating situation, and we'll see how how the current distribution is affected and what the radiation pattern and other characteristics will be, including the impedance. So you have to really solve for these reasonably simple looking, but in practice computationally heavy set of exercises to get the answer.
Right.
In simplest cases, you can argue, for example, if you take a simple dipole, you can work out its radiation pattern from very simple arguments. One is, as soon as you have a line, you can insist on cylindrical symmetry about the axis of the dipole, right? So you say, whatever I do, it should not differentiate between across the circle perpendicular to the axis of the dipole. Then you can argue that when I look at it edge on, that means when I see the line as a point, I should not get any power, right? Because there's hardly any radiator that I see. So just with these two conditions, and it should be maximum in the side that I see the full length. And just from this consideration, you can actually get the figure of 8 pattern, the Medu-Vada pattern for a simple resonant dipole.
can we also figure this out whether it's resistive or reactive from just checking the antenna impedance, the total impedance?
Yeah, if you take, assume, for example, that, with all these complex calculations, you have arrived at this result that half-wave dipole is purely resistive, right? Then you can use the corollaries to that. When it's slightly longer than that, you know that you added some additional metal, which will have inductive contribution, right? If you leave gaps, it will have capacitive contributions and so on.
Yeah.
So some heuristic, arguments can be used to figure out the sense of the way is likely to go. But the exact values will require to be computed.
Yeah.
Okay. There was a question in the chat.
Yeah, about the worksheets. I was about to address that. That's the one you're saying, right?
Yeah.
Okay. So what I was going to say is, I mean, these 2 weeks, you're going to have the most of learning, and it's best that you work on these worksheets during this week itself. You may not have to worry too much about finishing it completely, but try to see how far you can go with this, because if you put it off for later, you may not ever get back to it. So I would suggest that, I mean, of course, you can work as a team. That will make things go faster, and you can reach out to me through our channels, and I can help you with that. But at the end of end of the school, mm, I would expect that you just submit how much ever you can get through, you were able to get through, and you can give feedback as to these are the things that you didn't understand, or these are the prerequisites that you don't know. That's why you weren't able to go forward for individual sections if you want, and that would be quite helpful for me. What I'll create is a Google Drive folder for you to submit this towards the end. Worksheets in the evening slot. So what we're going to do is have another session in the evening slot next week. Next week, I think it is Wednesday or Thursday. Wednesday, no, Thursday, I think. So during that time, we'll go over how much you were able to progress. All you guys as team can let me know, and then we'll try to see what were the points where we were having difficulty, and we can help you out. So you have about a week, during which time it's best you talk among the group, and also get in touch with us through one of our communication channels. But we'll discuss this again towards next week. Okay, if there are no further questions, I think Desh can start his presentation.
Okay. So let me share the screen. Can you see the screen now?
Yeah, so back to the laptop.
Okay. So I'm able to move the. All right. Can somebody kindly remind me where I was lost when I lost the connection?
Can you go forward? I think, yeah, just before this.
I had probably talked about these, right? Reciprocity is where I was, or okay.
No, can you go back one more? Some more?
Oh, so I had not shown the telescopes.
No, sorry. You were, I think I lost whether I didn't understand you were going forward or backward. So
Yeah, that's
So
fine.
it's before antennas when you were explaining the array and everything. Can you go?
If I go back, this is
Yeah,
what.
back. Yeah, this is where you antenna
yeah.
and integral parts of the receivers. This is where you cut off.
Oh, I see. Okay. All right. So in fact, as you can see, mm, Prakash is coming in with the antenna details couldn't have been timed better. So, what I've summarized here is what he has explained in detail. Simple linear combination of the fields, right? at a distance can be worked out if you know the antenna characteristics, and I mean to get to know the antenna characteristics in near of our field. Right, and then I was saying, okay, so I can probably continue from here. Is that okay? Hello.
It's good, actually.
Yeah.
Please carry on.
Okay, all right. So the field aperture telescopes have traditionally been used with only one sensor at the focus, or even when you use a phase array with a large number of elements sampling the wavefront incident on it, and the sensed output is combined. Typically, people have been combining that to form only one output. So it's an equivalent of a single pixel camera. And you can imagine how difficult it will be, or painstaking it will be to scan a picture with 1 pixel at a time. So you have to devise some ways of scanning across the area, in this particular case, the area of the sky, while you can look at only a small piece of it at a time. So imaging by raster scanning was a routine thing. It's also helped by the Earth rotation, where you stay put at one declination or something, and at that declination, the entire right ascension range becomes accessible over the 24 hours, and then you can change the declination next day and do the same. And this is how you can row-wise sample a matrix and put the information together. So these are the telescopes that I was showing you one of the, starting from the left top. Now I have an advantage of the cursor with me. So this is the Groth-Reber backyard telescope that he built to go to higher frequencies. This is the RRI millimeter wave telescope, which doesn't exist anymore. This is the all familiar GMRT dish. This is the Jodrell Bank telescope, Lowell telescope. This is the Green Bank telescope, which is 110 meter diameter. This is the Arecibo telescope, which got damaged, unfortunately, recently. This is the Uti telescope, which is ingeniously built on a slope of a hill with the slope matching with the rotation axis of the Earth, so that one-dimensional movement can track a source. This is the Gaurividnu telescope, which I have played with a lot, which is a 1.5 kilometer long array, which has a huge collecting area, works at 35 megahertz, very long wavelength. This is the Mauritius Telescope, which was set up to study the center of our galaxy and the part of the galactic plane from Mauritius, which is a joint collaboration of IAA, RRI, and Mauritius University. This is an array of antennas. Example, this is the MWA tile, which is also something that we are using as a phase 0 antenna for the SWAN initiative. So essentially, you'll find that you have focus either as a point in all these cases, or as a line in the case of the Uti telescope. And here there's a virtual focus where the signal sensed by different pieces of it, elements, are combined together by hand. Here the optics takes care of combining them at the focus. This is the biggest single aperture, fast, just come about in the recent times. It's a 500 meter diameter, but this is not steerable. So I think Prakash has already talked about this, so I will just quickly go over it. In all our discussions, we will presume reciprocity as an implicit aspect where whatever we understand in the transmission characteristics of the antenna are exactly relevant as when you use that as a receiving equipment. So the aspects of aperture elimination, in the sense, if you have the dish or something like that, or an array of antennas, you can decide or design things such a way that different pieces of it get different weightages, and of course you want cutoffs of the radiation that you send from this focal feed to to make it smaller and smaller towards the edges, so that beyond that, which cannot be sharply cut off, you are not losing much energy to the ground. People can design that profile, how it cuts off as a function of radius, how sharply it cuts off, and so on, by designing appropriate fields. Point focus is never a single point. Thanks to the uncertainty principle, you will find that it has a size of lambda times the f by d ratio, as it's called, ratio of the focal length to the diameter. You will find that that is where the converging rays, instead of in ray optics, you might imagine that going through a point, which you might label as a focus. There is a patch, so bundle of rays converge, but they never come to a point in a real situation. They come to a very narrow spot of this size, and then diverge again. So those things are called the waist of the beam, and that's where you will have highest concentration of spatial concentration of the power received from such an aperture. You will find in all this, be it lens or be it a shaped reflector, which is trying to focus things, you will find the phase space density of the radiation is constant, or photons is constant. So that's Liouville's law, and you will find implications of it very easily in terms of when you have a wavefront where there is confinement in the direction because all the rays are parallel to each other. You have a width over which you sample the wavefront. When you try to converge it, that piece or that radiation into a focal point, you will find that now you are squeezing the spatial coordinate, but it has expanded the momentum spread. You will find the directions approaching the focal point are spread over appropriate angles. So anyway, those are details that, and some of it as constraints that you cannot violate. So you will find that the feed elimination pattern is to be matched, while when you actually have put your feed, you want to cover that spot over which the energy is available to get the maximum power transfer to the feed. People have advanced sense, as I said. You have many pixels now. There are, as somebody yesterday mentioned in some other context, the 144 pixel cameras are now made at radio. You can, this is a picture of the 7 beams of what used to be an alpha instrument on the Arecibo telescope, where you can make measurements in 7 directions simultaneously. Similar feats exist at Parkes telescope with 13 pixels and so on. Other telescopes which have got large number of matrix elements of these pixels, matrix of these pixels, and you can get up to what this particular one has, probably 49 pixels. So people have advanced in various ways, but you can also get multiple pointings by a technique that we're going to describe later, where you have array of dishes and elements on the ground, and you combine the information from them in a way to produce ability to look at various directions simultaneously and distinguish them from each other. But in doing all this, the signal that we pick up with our antenna element is so weak that it needs boosting by many orders of magnitude. Yesterday, some in our discussion, some of you actually would have done this calculation, and you would find that the powers, even with decent bandwidth, would be typically of the order of minus 110 or 120 dBm. Now, to get it to a reasonably recordable level of at least a few millivolts sort of voltages, you would require these to be amplified by typically 100 decibels. Now, in doing so, you will have to pay a price. Whatever device you use might add its own noise because it's at finite temperature. There is random fluctuations occurring due to in the equipment itself, and that can be sum totaled and represented by an equivalent temperature associated with that noise power as T receiver. What you require is also coherent amplification, in the sense you do not want to vary the, you do not want to change the information that you have received, mix any aspect or information at one frequency with another frequency in the band, because you would like to study them separately. So you need coherent amplification, where it's in olden days they used to have audio amplifiers which were called high fidelity amplifiers. What it meant is at each frequency you have only a scale factor describing this amplification. So you might have a scale factor which might depend on frequency, and the input and output are related by this simple factor. So as I said, we desire amplification, and the price we pay in terms of additional noise that we add in addition to what we have from the antenna. So the typical receiver chain looks like this. You have some kind of transducer which gets the signals translated into electrical signals. You have initial amplification, which you pay a lot of money or efforts to ensure that it does not produce large amount of noise. So these are called low noise amplifiers. Then you select the band of interest that you have by putting appropriate filter. These are analogous to the filters used in optical, where you choose the color appropriately. But in this particular case, it will be electrical circuits with inductors and capacitors and resistors, which will affect selection of the band of interest. When you have the signal coming through, for convenience of choosing any subsection of the spectrum and not having to change all the other equipment based on that selection, you can effect a conversion of frequency, where you have something in the spectral band that you want to look at. You can always translate that information into a convenient fixed frequency. In this particular case, for example, 150 megahertz is that chosen frequency to which you translate any information coming at a selected band to 150. And so if it's coming at 1420, you choose a local oscillator or local tone where you multiply this information with a sinusoid. And you can see that if this signal itself is thought of as a combination of sinusoids at different frequencies, each one of them will multiply with this sinusoidal function. When two sinusoids multiply, you know that from your trigonometry that you can write that as sum of two sinusoids, one at a frequency which is sum of these two frequencies that you multiply, and difference in the two frequencies. So you can arrange either the sum or difference to be the frequency that you want. So by choosing the appropriate local oscillator, you can, which is in this particular case, different by an amount that you want finally as an output, you can pick a particular band. And so this is called the RF, this is called the local oscillator, and this is called the intermediate frequency. The intermediate frequencies are chosen so that you can have the rest of the operation of the receiver at a fixed frequency. It's also useful in a very important way that when you amplify these signals by 100 dB or so, even a small leakage here of the signal would radiate in terms of radiation leakage from any one of these components would travel to your antenna and get picked up, and that will be way stronger than what is being received at the, from the sky. And this way you might actually have local feedback, and the feedback based on the sign of the feedback can result in either oscillation or saturation of the signal at this location. To avoid all this, what you do is you allow for people, this is like the movie theater. When you go to the movie, you cannot see the movie again on the same ticket. So you entered with the correct ticket here, you've been allowed in, and then something is done to the ticket after you go further, so that even you leak out, you cannot enter back again. And this is beautifully done by changing the frequency where while this frequency was allowed in, the translated frequency, which is at, let's say, a different one, this is not allowed through the main gate of the system. And so you can happily amplify these signals without worrying too much about radiative leakages in the process of amplification. All right, then you select the band, and then you can have even another translation for other conveniences that you might have. And then typically these days people convert the analog signal into a digital form, and which can be recorded onto computers, and then you can do further analysis and so on and so forth. So this is the typical receiver system or the electronics that is associated. You don't have to remember any gory details about it. The only thing to really remember is you should know how much amplification is required. You want it to be coherent amplification. That means it should really represent what was at the input. It should have utmost similarity with what the input, except the amplitude. I will skip over these details. We can discuss this later while choosing the amplifiers. You may have not heard of amplifiers at optical wavelengths as much as you hear in radio routinely. And that is because there is the amount of noise that inherently a device, amplifier device would produce is in the best case limited to the quantum noise. And so in the case of, in terms of exact description, it will typically have one photon equivalent in per phase space cell. In this particular case, the per hertz per second unit will have one photon equivalent noise. Now this in the case of optical turns out to be very high amount of noise. And so it's not profitable to use amplifiers at optical wavelengths unless, I mean, when particularly you're looking at the sky signal. In the lab, of course, you can use it because the signal that you might be using might be much strong compared to this noise. So so you will find that the phase coherent amplifier automatically puts the signal into the Rayleigh regime, where the wave noise dominates. So this the nature of this noise is also same. You have random Gaussian noise, which is added by the amplifier, which is almost indistinguishable from what you get from the sky. So you have to do some difference measurements or differential measurements or ways of measuring this noise to eventually subtract its contribution before you can infer what came from the sky. Please remember that the phase coherent amplifier is not a detector. It's just authentically scales the signal that is given at the input and gives a simple scale version at the output. We have already touched upon this aspect. Maximum power transfer requires impedance matching in any circuit, and this is not just limited to electrical circuits. Even when we have the feed and looking down on the reflector, you have to worry about maximum power transfer, and you have to match the characteristics of the feed to the reflector so that power is not wasted and it's really radiated on reflection in the correct direction. Impedance matching is also important while I'm actually talking to you. Unless we are really coupled well, whatever I'm saying might just get lost. So impedance matching is a very broad concept for maximum power transfer. What happens if you do not match? There will be reflections. There will be not everything will get absorbed in the way you had desired, and the reflections in the cases of signals will interfere with the forward going signals, and you will find that it leads to interference of between the two, or superposition of two will decide how the net signal will vary, and that you will find leads to patterns which are called standing wave patterns. They will exist both across the space dimension as well as in the spectral dimension, because after all, the interference depends on the relative phase differences, and the phase differences will depend on the wavelength and the spatial dimension. You will find the prices will be paid in terms of loss of signal and efficiency of your setup in general. So you will find it can happen even in the way you might do software analysis. Analysis using certain software. If it's not matched to the kind of characteristics of the signal while you're trying to detect a certain pattern or certain attributes of the signal, if the improper mismatched filtering that will happen effectively will lead to you losing the ability to detect that particular aspect for which you're doing the analysis. So please keep this in mind. The optimum way to get a result out of something is to match, pay a lot of attention to the matching aspect of what you're looking for and how you are looking for it. So we already answered this question. The only part I want to highlight here, which I have written in different color, is the coherent amplification also implies there is linearity in the system. By linearity, one means that when I change the input by a certain factor, I should see exactly same factor increase in the output. The association of, so that the measurements of the output can easily relate to how things were at the input, and any changes I see at the output are easily attributable to a genuine increase in the input rather than something else. So those require a lot of care in designing the receivers. It's not easy, and there are people who are masters of designing such things. What happens in linear systems is if you can send an impulse, a delta function input to the system and ask how the system will respond. And these are typically used as descriptors of the behavior of the system, and they're typically known by this name, impulse responses. You will find for a linear system, all the inputs, if we were to imagine them as made of a set of delta functions with different heights coming at different times, which is very acceptable description of the input, we can choose these delta functions as finely in time as you want. Each one of them gives rise to the characteristics that are described by impulse responses, which are scaled by the height of the delta function at the input, and the timing reference to when the delta function is given as an input. The output can be described as a superposition of impulse responses corresponding to each one of the impulses at the input. When that description holds good, you will, this is what is required for linear system. You will find that the output is a simple convolution of the impulse response with the input pattern. And this is something that you can use profitably to understand how the system will behave to a certain input. Okay. And as I said, whenever you're trying to detect something, you will have to ensure that you're doing any choosing or any analysis operation which is amounting to selecting things, which is, generally you can call filtering. You have to look for the pattern optimally so that your output, which says yes, you have found it, is really representative of the fact that you exactly found the pattern you're looking for. So it's another way of saying it is when you suppose you want to choose you want to find out whether this key is similar to the one that you have. One easy way is to design a lock or take the lock that your already available key opens and see the new key is able to open that or not. And so the filter, the way you detect the desired is by designing a conjugate filter. When you want to see, so the conjugate here is the lock, and you want to look for the same key, and so you design a filter or a selection criteria which is based on the lock, which is a conjugate filter. And this is something that you will encounter in all aspects of detection, regardless of whether it's astronomy or elsewhere. And it turns out in the presence of Gaussian noise, random noise, match filtering is the best detection technique. Okay. We can now ask how sensitive our receiver or the system is, how faint an object we can detect. And that depends on the number of photons that we have collected in the bucket that we have per piece of information that we will record independently. And each piece of information, independent piece of information, is available to us at the rate given by the bandwidth. That means if our bandwidth is so many hertz, we have independent piece of information coming at intervals of inverse of the bandwidth. We can use this advantage that we have independent pieces of information coming at individual intervals. We have seen that individual pieces of information have the required information in terms of the mean value, but it also fluctuates by an amount which, thanks to the exponential distribution, we know that the fluctuation is 100%. The mean and RMS, the mean is our desired parameter, but it can fluctuate by an amount which is the standard deviation typically, and that itself is equal to the mean. That means we have 100% uncertainty in each one of the measurements that we make at intervals of inverse of the bandwidth. How do we get to the estimate of the mean that we want to have? And this is where the uncorrelatedness or independentness of individual measurements coming at intervals of 1 upon the bandwidth will actually help. It's like asking large number of people. Each one of them might give you an erroneous answer or a correct answer, but added with some truth, the same truth, but different amount of lie. If you ask large number of people, you need to take an average of what they have said, you will distill out the truth. And this is exactly what we do. We know that each one of the pieces of information has the mean value and some deviation from it. And the deviation is random. The deviation in one sample is not related to what the next sample looks like or any time later. And so we can treat all these as independent measurements and combine them. And when we do that, you will find the number of such samples can be described as the time bandwidth product. Simply that per unit time, we have number of samples which are equal to the bandwidth, and the amount of time over which we collect this information will give you the time bandwidth product. So the number n, the number of independent samples you average, is simply described by the time bandwidth product. So you can see that these days, even with large amount of noise in the receivers and in even in the sky background, you are able to make detections at sub-millijansky level, where the Jansky unit is as described earlier. So you can rely on using large bandwidths and long integrations to make more and more sensitive measurements. This is in addition to collecting large number of photons by using large collecting areas. So the radiometer equation, as it's called, which describes the sensitivity of a telescope, is formally can be written like this. We will work in temperature units, but you can also use some other units if you wish. So this is essentially the equivalence of intensity or power. I'm trying to get my cursor down. Yeah. So the RMS fluctuation that you would see against which you will be assessing any presence of the signal that you might be looking for, it has to be few times the RMS for it to be not considered a chance fluctuation of the random variations that you will generally see. And this is calculated by accounting for efficiencies, if any, that you need to account for. You will have system temperature, which describes the total amount of noise fluctuation, noise power that you have in the system, which includes what you get from the antenna and what you add as a part of the receiver. And then, as you said, this is the amount of noise that you have, and for each sample independent piece of measurement, which is done over a duration which is inverse of the bandwidth, you will have 100% fluctuation. So you will find the fluctuation will also be of the same magnitude as the mean that you are looking for, which is the thesis. And so the time bandwidth product, square root of it, will decide the way the fluctuation will reduce when you integrate or add together large number of such independent pieces of information, each coming at the interval of inverse of bandwidth. So if you integrate for a time t, you would have got delta nu times t int as the number of samples. You could also add additional factor of number of polarization measurements that you have done, which if you want to add them together, NP can be 1 or 2 based on whether you made independent orthogonal polarization measurements. So this number is the number of independent samples you have averaged together. You got an advantage of reduction in the RMS by an amount which is 1 upon the square root of the number of independent samples. And this is the essence of the technique to make your radiometer or measurements sensitive. There is no other way of than having increased area and so on. So you'll find that you can see the relative importance of the wave noise, and so what all the considerations that we have of exponential distribution and RMS being the same as the mean at the very raw level are referring to the so-called wave noise. You could also have domination of counting noise if when the number of photons is rather small, as in the optical case, but we will not dwell on it too much. Except to remember that in the radio telescope cases, even for the weakest radiation, we always are assured of the large number of photons. You will find the number of photons times h nu will give you the energy, and that is what is proportional to the system temperature. We can equate it in temperature units. So this includes the receiver contribution, the antenna signal represented as effective antenna temperature or power associated with it. You might also have background contribution, and then you might have spillover in the sense you might have in the dish case, when the feed is looking down, what it's receiving is also beyond the edge of the rim of the reflector, which is at certain temperature, which might be at ambient temperature. And that is also radiating noise, which you might pick up, and all that is accounted for in the system temperature. Of course, you would like to minimize all these contributions except the antenna temperature. This is what you would like to boost as much as possible. It turns out that for faint sources, when the antenna temperature is rather small with respect to the receiver contribution, the background contribution, the spillover, and that's what decides the RMS fluctuation that we computed. So in that case, even if you keep the background and spillover less, you will find that your signal to noise ratio or the performance of the sensitivity depends on the receiver temperature. And if you would like to so which is of course independent of the collecting area, but you would like to boost your antenna temperature by collecting more photons from the source, and so the signal to noise ratio will then be proportional to the effective area. When you have a very bright source, when you have ample number of photons, you will find the fluctuation, the system temperature is then dominated by the antenna temperature itself. And now you're dealing with the fluctuations in the signal of interest itself. They are identical to what you had in the earlier case as well. But now you're fighting with its own fluctuation. And there you will find that beyond a certain point, the bucket size does not matter at all. And the signal to noise ratio you will get is simply decided by the number of independent samples you can average and build up the contrast. So, all right, when you look at the source, you will find the radiation coming from a source might come from a discrete point source, or it might come from a slightly broader source, but a discrete source which is localized, or you might get you know, a very extended source may not be as compact and may not be as extremely compact like a point source, which is unresolved. So you might get radiation from these, or you might get radiation from background, which is extending over large solid angle from everywhere, like the 3° K background. So at any given time, you might get contribution from all these, and based on the situation, you can estimate how your antenna would respond to this. So the antenna temperature, as we have seen, is the measure of the power that we have actually received, and then we try to equate that to a fictitious situation where we say, if I have a resistor and if it has to produce the same power that I have received from my antenna setup, what should be the equivalent temperature of this such a resistor? And this is something that you are going to look at in one of your worksheets, so I'm not going to dwell on this pretty much. If you have, as we say, a source which covers the entire view, we can argue from simple arguments that it's as if we are sitting in a heat bath. It will appear like we are sitting in a heat bath, and the antenna temperature will be same as the source temperature in such a case when it's fully covered. If it is covering only part of our view, then you will find that you will have to do the averaging, and so a bright temperature spot of smaller angular size, its contribution will get diluted effectively when you try to find an average temperature across the beam. And so this is what can also be used to quickly estimate the antenna temperature when you're looking at a source. Okay, the antenna response, although we would like to have directivity, which you know, very ideal, where we look at certain sector, we want to assume that it's not looking at any other part of the sky. You will find that this is not true. While we look at some direction sector prominently, we are also looking at with a little bit of response in other directions, which are called side lobes. When you want to look at any one source of interest, you are not guaranteed that that's the only source in the field of view that you have. You might have other sources also present, statistically speaking, based on the the solid angle that you're looking at, and how the sources are distributed in the sky, and which sources you can detect, which sources you can not detect discretely, is based on your sensitivity and the resolution together. And when the resolution is poor, you suffer from additional uncertainty due to what is called confusion, and you will find it depends on how the distributes how they are distributed in intensity. That means you will find, if you look at what is called log n log s relation, this is the relation of the number of sources with certain flux density, or flux density greater than certain limit. You will find that it's a power law, and you will find large number of sources with smaller intensity in the sky. Although they might be the ones that you want to study at given resolution, they might be a nuisance when you want to study a particular source or estimate its intensity. You have to also take into account what other sources were there in the field, because you cannot tell them apart, but you can estimate statistically what might be the typical contribution they might be making. So your sensitivity not only depends on the formal thesis divided by square root of time bandwidth product, that kind of expression. It also depends on how clean your measurement is, what are the other sources of confusion that you might have. Okay, I think I've gone through this. So this is the case that I was describing when you have a very strong source in radio. You will find the system temperature, the entire noise budget is dominated by the antenna temperature. It's much higher than what the receiver is contributing. In which case you will find your ability to detect weaker signals or the RMS fluctuation that you will have to live with depends entirely on the source characteristics and the time bandwidth product. You will find the area of the dish or the collector does not figure in here at all. In the optical case, however, when you're starved of photons, the number of photons depend on the area of the collector, and you will find that there the noise fluctuations are dominated by the counting noise, where they are you get better and better situation. The fluctuation in the number to the number that you want to detect is given by 1 upon square root of n. And so you will find that this contrast of n with respect to delta n improves as you use bigger and bigger diameter lenses or mirrors in optical. Okay. Now, this I already said, what rate are we getting independent pieces of information? We get that, as I said, every new piece of information at the interval of time, which is inverse of the bandwidth. And so over a time duration delta t with bandwidth delta nu, we will always have the luxury of having delta nu times delta t independent pieces of information. It's also, this is not the only domain in which information is available. It's also available in the spatial domain. You will find you collecting information over a range of the size of the aperture, and you will find that is also a domain in which information is to be considered. So you have two pieces of information that you're looking for.
Banking frauds. Airtel will never ask you to share OTP or change your email ID on your account. Stay alert.
Sorry.
The number you are calling is currently switched off. Please try later.
Was that from my system or somebody else's? Hello?
Yeah, it sounded like a phone call.
Yeah,
but it
looked like a
did-
phone call. So my phone.
no, I heard the word OBS. That's the software we are using to stream. I was wondering whether we are having some problem with that, but you can continue. We'll try to sort it out.
All right. So yeah, so we have bandwidths of two kinds. The information content where the fluctuations are in time, and there is also bandwidth in terms of spatial frequencies, and that is measured in units of distances divided in units of lambda. And this is relating to the aperture domain. And this is what we will find that there is a Fourier relationship between that spectral domain and the angular domain, which is what we're going to exploit. So what we have seen in terms of resolution, the limiting angular resolution is related to the inverse of the span in the spatial domain. The lambda by d expression is basically a reflection of that. Okay. The spatial frequencies also depend on the temporal frequencies because of the common thing of lambda here. Okay. So in general, you will find that all that we will be doing in terms of increasing our sensitivity or ability to get finer information with some confidence will depend on how many pieces of independent information we have. And that is because we are looking at a phenomena which is described best by random fluctuations, and we are trying to infer statistical properties of it, in this particular case, the variance of the noise that we receive. So we will always have to depend on independent pieces of information and how we can combine them and how we can build up confidence in detecting deviations from in the means that we compute. Okay. This is, I think. All right, so just to remind, we mentioned that we have been using single pixel cameras in the field aperture cases, and the painful raster scanning is a very laborious way of making images. So we can do something better, and instead of, ideally what we require is to build a big telescope to study the sky at very fine resolution at radio wavelengths. It's a daunting task, almost impossible to get the same kind of resolution as our eye has at optical wavelengths. If you translate that, the same lambda by d, where lambda has increased by orders of magnitude, you will find you will require a 10-kilometer radio eye to get similar resolution that we are used to at optical wavelengths with our human eye. Now, such a telescope cannot be built as single piece or steered and so on. So what we do is we, instead of making measurements in the angular domain, we try to make measurements in its Fourier domain. So these can be understood at holographic measurements. It's like measuring Fourier components of the distribution of the sky. We can easily imagine any distribution, in this particular case, bright intensity distribution in the sky, can be thought of as superposition of large number of sinusoidal patterns. And if we can measure each one of the sinusoids with its amplitude and phase, we know that we can reconstruct the picture by superposition of such things. It turns out that each one of these sinusoid and its amplitude and phase can actually be measured. And that measurement involves using a pair of antennas and asking how similar the signals received by the two antennas are. Formally speaking, we look for mutual coherence in the signals that are received in the two locations. And this amounts to actually measuring one Fourier component, or one filtered sinusoidal pattern in the composition of the sky. It effectively amounts to multiplying the sky brightness by a sinusoid and integrating over the sky and getting one number, which is a result of this product and integration. As you have seen, this we will relate that to a young double slit experiment where you know that you will see a fringe pattern. So the fringe pattern is exactly equivalent of this sinusoidal pattern I'm referring to. Now you can ask how many pairs you can get. If somebody gives you n antennas, you can get NC2 independent pairs. So you can make n into n minus 1 by 2 measurements of the Fourier components. By ensuring that you don't measure the same Fourier component twice, that means avoiding redundancy, you can cleverly arrange your apertures or sensors in a way like in this example, or in the case of GMRT. You can arrange them in an optimal way, such a way that each pair of antennas measures a different sinusoidal pattern with different orientation and different periodicity. So by doing that, you can measure large number of Fourier components. You can also use Earth rotation to measure different situations, even with a single pair of antennas. Because if you put the pair of antennas along the east-west, for example, as the source rises at the horizon, it will see the line joining the two antennas as simply a point. So you have made it appear like a separation which is zero. It's only when the source comes overhead that it sees the fuller extent of the separation between the two antennas. So you can, using the same pair of antennas without moving them, using the source direction change, you can make measurements as if you made measurements with different separations between the two antennas. You can also imagine that if there is a source at the pole, it would see the separation, the line joining the two antennas rotating with respect to its nose. Suppose the source had a face and a well-defined axis defining its nose. You will find that the line joining the two antennas on the Earth will appear to rotate with respect to the nose of the source. And so you will find that with one pair of antennas in the east-west direction and source rising at low declinations, you will find that you have actually made measurements along all the measurements that you would like to make along a line. In the other case, with the tip of the vector joining the two antennas, making a rotation that a source at the pole would see, you have made measurements that you would like to make along a track, which is a circle. For any in-between case of source direction not being at the pole and not being at the equator, and your antennas also not being separated exactly along east-west or north-south, you will find that the typical track of the measurement you do of this vector separation will be along an ellipse. So you can get, by using Earth rotation, measurements along an ellipse. And such ellipses put together might fill all the information space that you would like to sample. I'm describing these in words. We will look at pictures relating to this pretty soon. And this way we can get all the information in the Fourier domain corresponding to a big aperture, and then use Fourier transform to translate that back into the image. Without going into all these details, we can ask also a very simple question where, imagine a big dish made, a fictitious dish made. We can ask what we are receiving at the focus of such an imaginary dish. We will receive information which is coming from different small sub apertures which constitute the big aperture. Let's label them as E1, E2, E3, E4, up to En, based on the n pieces that we want to consider for this illustration. So big aperture made of n small apertures is what we are looking at. We know that the electric fields that we have in these different parts of the wavefront that we receive are brought to the focus, and we get the sum total of this. What we are interested in is the modulus square of this electric field, and that amounts to multiplying the total electric field or the signal that we receive proportional to the electric field multiplied by its complex conjugate. So from your simple maths background, you will know that this product, where individual E total itself is a sum of large number of E's and multiplied by its complex conjugate, you will find it can be expanded, and you will find all the description of this expanded version can be described in terms of pairs of cross terms. Cross terms which are multiplication of EI times EJ, I running from 1 to n and J running from 1 to n, EJ star. So essentially you will find that the measurement that you wanted to do can be expressed in terms of sum of products, pairwise products of electric fields received by different pieces of antennas. Now, this is exactly what a 2-element interferometer would measure. So you require a large number of 2-element interferometers to measure all the possible terms in this. And when you sum them together, you will get the intensity that you are looking for. But having measured these pieces separately for sub-apertures, you have the advantage that you can add them in with different phases also, and that would amount to getting the electric field associated with another direction. And this way you can, using the sub measurements of these products and putting appropriate phase shifts before combining them, you can make the instrument look in different directions. And this is how we can make images, by making these pairwise measurements of electric field products. So this is what we're going to illustrate. There are many telescope arrays, which are the first such was big one was the Very Large Array in New Mexico. We have now GMRT. So essential point here is in this what is called synthesis imaging. What we are doing is synthesizing the aperture, a big aperture, by using small apertures and using them cleverly to make measurements which are component measurements in the big measurement that we want to do and add them together. The essential assumption in all this is that the sky distribution that we want to study is not varying in time. And this assumption helps us to make some parts of the measurement now, some parts of measurements tomorrow, some parts of the measurements day after tomorrow, and combine all that together because they correspond to the same brightness distribution that we wish to look at, and we can assume that it has not changed from today to tomorrow and so on, or even routinely that we do within a day, it has not changed. So with this essential assumption, we can measure the similarity between the signals received by a pair of antennas, which might be separated by different distances from with different orientations. So each one of them, when we measure the similarity, we note down that number. And that measure of similarity is what is plotted here. So starting from the center where the separation is 0, and the orientation is for any other pair that we're going to consider away from 0, we will have a specific orientation. So if the pair is separated like this, and we measure a certain similarity between the signals received by the two, we note down that and mark a point here. And same way as is done here. And so we can fill this space. If we fill this space to the level which is labeled in units of wavelength. So suppose we measure it to 100 in units of lambda. We have information over that extent. Inverse of that scale defines the resolution that we will get. So we can go and fill this information up to whatever is the extent of the separations we can achieve, which in the case of GMRT can go up to 25 kilometers. We will have information filled in this domain. And then all that it requires is to Fourier transform this information. I'm trying to find a cursor. Yeah. So Fourier transform this information and you will get the image of the sky. So because you could not measure this directly with fine enough resolution because you didn't have a telescope like this, we used the description of it in the Fourier domain and asked whether we can measure that. And that became measurable with a large number of pairs of antennas and including you exploiting the rotation of the Earth to see the same pair as you know, in different orientations and different separations, allowing us to make measurements of different points in this plane using the same pair. Okay, in all this, we are using some concepts which, as I said, we are measuring the similarity between the signals. And really what we are trying to measure is the coherence in the signal. Coherence, many people understand just as, you know, described as two things are coherent if their phase difference is constant. That's the definition many people tell me. But it's much more deeper than that. And you will find that coherence can be assessed by, in practice, we assess it by correlating the pieces in which we want to assess coherence. Correlation is a technique to find similarity between the signals. Many times, many things that might appear dissimilar might still be coherent, but if they are incoherent, we are certainly going to find no correlation between them. So you will find that lack of coherence would lead to lack of correlation. That means there won't be any similarity between the two things if they happen to be incoherent. But the converse is not true. So while we are trying to look for coherence in signals received at the two locations for making these pairwise measurements, we need to remember that while the correlation might be formally small, that is not the full story. we should look for possible effects that might make things look somewhat different, but if certain things are accounted for properly, they might be actually same, and they might be then showing high degree of correlation. And I will give you a very simple example of it. When a particular two observers looking at the same source, one in Australia and one in India, looking at a source which is setting in Australia. I think if it's setting in Australia, it might be overhead in India. So you will see the Earth rotation vector is now perpendicular to situation, the direction that we see in India, whereas the telescope in Australia is moving away along the line of sight of the source. And so you will see Australia observer will see a Doppler shift in the signal that is received. So even if a single tone was radiated by the source, you will see a Doppler shifted version of it, whereas the Doppler shift for an Indian observer would be 0 because it's moving tangentially. Or direction perpendicular to the direction of the source. And this would now lead to two sinusoids which are at slightly different frequency. And if you compute a formal correlation between this, you will find that the net integral of the product of these two sinusoids is 0. So you will find that you should not blindly throw away that as saying there is lack of correlation and that implies lack of coherence. You would have to do the right things to bring them to the same level so that the comparison is fair. So you have to account for all these effects that might change the appearance of the signal. In this particular case, I gave the example of the Doppler shift. They might be simple things like they might be even locally two antennas looking at the same signal might have, one of them might have some phase shift of 90 degrees and two sinusoids with 90-degree phase shift will show no correlation formally. So what you need to do is account for that phase shift and then slide one over the other and then compare. So while assessing mutual coherence, you need to be mindful of all the scalings that you need to try or account for and any translations. Now, while in time I just described the scaling with a phase shift amounting to a shift in time, you can also think of the Doppler effect compensation as a translation in frequency. So scaling in both the time domain as well as in the other domain, its Fourier domain, have to be taken into account. It's like almost saying that if I look at an apple, a picture of an apple, and the apple is moved in another photograph, I'm trying to look for coherence between these two pictures. Do I worry about the fact that it's shifted? Of course, you take that into account while making the statement whether the two apples in the two pictures are same or not. So you allow for scalings, you allow for rigid translations along both the axes, X and Y axis, in both the domains. What are the two domains? Whatever domain you're getting the picture in and its Fourier domain. So once you do that, you will find that you might be in a better position to assess the similarity and use that measure formally of correlation to assess the coherence. In general, two things are mutually coherent if I make a copy of it, copy of a given description in phase space, and then make any modifications to it which are reversible, then you will find the coherence is still not destroyed. But if I do any translations or mixing which is undoable uniquely to get the original description in phase space, then I have destroyed the coherence. So you will find the mutual coherence is not destroyed through any reversible translations or operations. So this is what the heart of this. Is it a good time to stop? I've sort of lost track of time completely. This might be a time to stop and ask if there are any questions.
Hi, Desh.
Hi.
Hi. No, you can continue a bit because I think Prakash's presentation will probably shift it to the afternoon, either before yours or after yours, depending on what you mutually agree.
Okay.
So I think it'll become a bit too heavy. So you can take it to whatever level you feel comfortable and round it up. That should be fine. Okay.
So yeah, since this is my last talk, I will like to take it forward. So what we have is the analogous situation that the pairwise measurements that we want to do are exactly synonymous with the Young double slit experiment that we perform. You will find that the two apertures that we will use in radio, they are also used in optical to make measurements of the source signal. Here they are made to interfere, and you see something on the screen. But in radio, we sense the electric field associated with the electromagnetic radiation received, and then make comparison between the two by taking one and multiplying by the conjugate of the other. And as I said, the correlation or seeing similarity is done by taking projection of one on the other and seeing whether the patterns match. This is done in the time and spectral domain as we have the signals. So essentially, while we measure the similarity, the situation is analogous to this, and it's equivalent to sitting on at the center of this viewing screen and making the measurement of the intensity. That will be equivalent of what we call the measurement of the fringe intensity. In fact, the context of optical analog here is what leads to the name called visibility in visibility measurements in the synthesis imaging, where we are really referring implicitly to the visibility of the fringe. So, for example, if there is a discrete source from which we get these, you will see clear fringes on the screen. If you use not a point source but a broad source, you will find the fringes from each one of the pieces of that broad source will appear here, but they will be staggered with respect to each other, and you will see this the clarity with which individual fringes are visible will be washed out, and you will get smearing of the fringes in the case of broad source. And so by measuring the visibility of the fringes, that means relative amplitude of the variation associated with the fringes with respect to the mean level of light, is the measure of the source intensity distribution. And this is exactly what we are trying to use. Formally, you can show that the pattern that you get is relating to the single slit property. Individual slits might have certain size, and so that describes the envelope of this pattern. And the fringe pattern associated with the double slit is modulated by the diffraction pattern of individual slits. So this is how you will describe the description. Describe this pattern, and what you will find as that this is the pattern in angle. When you look at your screen, what you are actually having is a diffraction pattern in angle, which you, to view that, you put a screen and at a certain distance, and you will find that the fixed angular pattern translates to a spatial pattern based on the distance. Out here, if you take a pair of antennas and add the two signals, you will find it has effective diffraction pattern, which has an envelope corresponding to the diffraction pattern of the single aperture, and within which you have this fringe pattern associated with the separation of the two antennas. Now, the two antenna separation can be thought of as a frequency component, a delta function in the spatial domain, in the spectral domain, of which in its Fourier domain, it represents a sinusoid. And so in the angular domain, a sinusoid will be corresponding to a delta function in the spatial frequency domain, to be not confused with the temporal frequency domain that we have normally used in time and frequency context. So you will find that this is the pattern that effectively corresponds to the response of a pair of antennas, and the sky distribution is as if it's multiplied by this pattern, and we get a net effect of the distribution. So this is what we are trying to do. We are trying to synthesize an imaginary big telescope by using pieces of the antennas which will correspond to sections of this imaginary big telescope. Of course, one has to be mindful of the effects that I said, which might appear to destroy the correlation. One of them is simply that if there is a source at some angle with respect to vertical, these two pieces will receive the same wavefront at not at the same time, but with a time shift, and or after having traveled some extra distance, which depends on the angle, some trigonometric function of the angle, and the length of the baseline, as you say, of the separation between the two antennas. So ideally, we need to account for this by delaying the signal that we receive from here, where the signal had arrived earlier, so that the patterns match if they happen to have matching. If the signal received here itself is very different from signal received there because it came not only from one direction but from multiple directions, then your accounting for the delay does not matter, and you also do not know for which direction you should account for this delay. You cannot simultaneously account for delays from various directions, that would be in picture for different directions. So this happens only when you have decided to pick a particular direction, you compensate for that delay. So out here, this will ensure that the correlation will not be reduced because you're not compensated for this shift in time. So what you're looking for is basically the information that is reaching you, the pattern of changes in the electromagnetic intensity in the field strength. Electric field is identical in both the cases, and if it happens to be identical, you need to account for the extra path traveled before you make the comparison. So you bring them on the same wavefront before making any comparison. And this is done effectively by, in the most complex situation, as one of the famous astronomers described, to a physicist, this can be described as two observatories, moving differently. You can imagine that the clocks in each one of these observatories also will be modified. So if you account for that properly, you will find that you have corrected for all the effects which would have otherwise destroyed the apparent correlation. So accounting for all motions of the observers is the key part that we are actually doing in all the details that we do in interferometric measurements, all the compensations that we do, and so on and so forth. Essentially, one wants to sit on the same wavefront so that one can exchange notes and make comparisons between what one received and what other person received, so that we can use this information to infer something about the source. It's the same thing. I've just written the expression d sine theta is the extra part difference, and we want to be on the equiphase surface, which is the wavefront at both the locations. Just because the wavefront comes from another direction, we don't want to be put in trouble while making the comparison. So we will make appropriate delay compensations or any Doppler shift compensations to make sure that we are not cheated by other aspects while assessing the similarity between the signals. So I will not dwell on this too much. You will find that you will get, when a pair of antennas is used, and you simply make a sum of the voltages which are proportional to the fields received at the two locations from a discrete source, you will find that you will see fringes at any given frequency, which is basically described, one such sample is described here, because it is going through ups and downs of the interference pattern associated with the combination of the fields received from the two. Based on the relative phase differences, you will do a constructive or destructive interference of the fields received, and that is what will show up in the sum of the contributions from the two. It will also be not same identically at all the frequencies, because phase difference depends on the frequency. The delay, physical delay might not is independent of the frequency, but the way it will shift the phase at different frequencies will depend on frequency, and that's what will change at any given time. You might find that it's a constructive interference at some frequency, but it's a destructive interference at some other frequency. So you might see tilt of these fringes seen in the what is called the dynamic spectrum in the frequency versus time diagram, where the equipment is kept looking up and the source is passing over it due to the Earth's rotation. So You can see the fringes like this with smaller separation in time or in angle when the baseline length is long. You will find sparser fringes when the baseline separation is small. So when these are longer baseline, faster variations in angle. These are smaller baselines, smaller separations, and slower variations in angle. So you can basically measure the intensity of these fringes and associate that with a Fourier component that you wish to measure in order to synthesize a big aperture. So you can have large number of pairs. I just to understand how much contribution you will get at any given time is to imagine a source or the brightness distribution in the sky. Imagine that being multiplied by a sinusoidal pattern, which is sinusoidal in one direction and constant in the other direction, orthogonal direction. What is the sinusoidal pattern periodicity? The periodicity will be dictated by the separation of the pair of antennas. If the separation is farther, then these fringes will be closer together. They will be varying more rapidly in angular domain. And so you have this sinusoidal pattern multiplying the brightness distribution, and then integrating this product is what will decide what you will get as an answer. You can see that if the source is bigger and it's covering many ups and downs, then the net effect will be zero. So you will find when the separation of the antennas is larger than a certain limit, where the fringe separation is comparable to the size of the source, you are beginning to get internal cancellation due to the across the fringe pattern. If this was a very compact source, just a point source, you will find it will sample only one part of this pattern, and you will get, depending on high or low, the intensity associated with that. And then the fringe pattern, you can move the real and imaginary parts of the comparison that you will do will be corresponding to the fringe pattern that is shown here, and the other one will give you the 90-degree shifted pattern. So if you see low intensity, if you happen to sample the low intensity point of this fringe pattern in the real part, you are likely to get back the lost part in the imaginary part or the orthogonal shifted part. And so you will not miss out on it at all because you measure the full information while measuring the visibility. Okay, I will skip this and probably talk about it later. This is the stuff I was describing in words earlier. You will find this separation AB of two observers seen by a source will be subject to how the source sees it and in terms of its orientation. If it has a preferred nose direction, then it's measuring the orientation and the separation of this baseline with respect to that reference. And you can see that typically you will, with a large number of pairs of antennas that you can construct using an array of like this, in the case of GMRT, you will see one of the baselines will measure, make measurements along all these points which are representing the separation in kilo wavelength along X and Y direction, which are labeled as the UV coordinates, the spatial frequency coordinates. So you would have made all these measurements during the 4 hour that you might have a look at the source. With another pair, you might at any given, if you take baselines for a given antenna with respect to all other antennas, then you might get 29 baselines given the total number being 30 antennas, and you would have sampled at any given instant all these points in the Fourier domain. With 4 hours spent with one antenna with all other antennas making pairs, 29 pairs, you would made measurements along these tracks. So it is like wanting to fill this entire area with measurements with a sketch pen which can draw ellipses or parts of the ellipses, and many strokes can be made based on the number of pairs you can have, and so you can make large number of strokes to fill this area. You can see that more and more strokes you can make, more and more area you can cover. And if you have taken care not to make a stroke over the same existing stroke and so on, you will avoid wasting your effort and rather use that effort in filling other space. So you can make many pictures of this based on the direction of the source that you're considering and so on. For example, this is a high declination source. You can fill pretty decently all this part of the space. Now you can ask how finely I should fill the space. Are these gaps okay? And that depends on the whether there is information that is missed out if you don't sample this in between region. The other way of asking the question is, if I make a measurement here and there, is it okay for me to assume that I know the information in between by interpolation? And that is decided by the rate of change of information in this domain. You will find that this is dictated by the width of the information content in its Fourier domain. For example, if you have want to confine to a certain sector in angle, inverse of that angular sector will decide the level of similarity or the scale over which the information might change in its Fourier domain. So this inverse relation always helps us to assess. So if you choose a sector, a window in the angular domain, it will tell us over what scale in the Fourier, its Fourier domain, which is the spatial frequency domain, the information is changing. Now, if you find that you choose a small enough angular sector, then you will find the information is not changing very fast over the spatial frequency domain, in which case it's perfectly okay for you to make measurement here and there and use interpolated information in the middle. So we, as much as some restrictions are put by the Fourier relations and uncertainty principles, we can also get lots of insights about the way we should sample, what is important, what we can compromise on, and so on, using those relations. So I will skip this. Essentially, you can measure these informations as visibility. That means the level of similarity between the signals, or the intensity of the signal that is similar as a function of the separation in baselines. You will have to account for all the instrumental effects before you can begin to use this information with some confidence. And you will find that what you'll be doing is, after having calibrated each one of these measurements, if you take data from individual baselines, individual spatial frequency component, and begin to put that in the image, And that is what you do when you take Fourier transform. You take each point and associate a sinusoid with respect to that and put that sinusoidal pattern in the other domain and keep superimposing these patterns to get a complete picture. And so what you'll find is in the right ascension declination in the angular coordinate, you can take a particular baseline and put the pattern associated with. What you have done is the earlier measure of level of similarity between the signals is used to scale the amplitude, and the complex information, the complex visibility that you had measured also had phase information. So the way the phase shift of this pattern has to be arranged is known. The orientation of this pattern is decided by the way the baseline, the line joining these two antennas was oriented. It was oriented this way, and so the pattern will be in that direction. So having put this pattern over the patch of the sky that you want to study, because you had this measurement, you knew the amplitude, you know the phase, and the orientation of this pattern, you can keep on looking at different baselines, and you will find that they give you different patterns. When you begin to combine this together, you will find the picture emerging as a result of the Fourier transform, and this is the picture you'll get. Of course, this looks, although this is a nice bright source which stands out well above this other junk contribution, you will find that this junk still physically exists, and it is a result of you not having made all the possible measurements that you would have wished to make. And it's a result of that inadequacy, which you can account for using appropriate techniques called clean, and you can get a beautiful image of that piece of the sky. In this particular case, it happens to be a nice compact source. It will never appear like a dot, a point. It will have a finite size in angle, and that angular size will be now effectively the inverse of the effective aperture you have built through these measurements. So if you have synthesized an aperture by using these pairwise measurements over 25 kilometers and you're working at 1 meter wavelength, you will actually have 1 upon 25,000 radian in, as an angular resolution in radians. And so that's a very impressive way of doing it. So as I said, interferometers have a nasty point spread function. These responses, which are a result of having measurements only at certain locations. In Fourier transform, this windowing pattern results in a response which has not just one individual peak that you would have liked to have at a certain finite width associated with your resolution, but it also has lots of side lobes and ups and downs around. So one can deconvolve this. What happens is for every point in the image, you have this replica of the point spread function appearing, scaled by the intensity of the of that particular source. And so effectively, it's a convolution of the true brightness distribution with this point spread function. So you can use deconvolution techniques, which are not always trivial based on the complexity of the field you're looking at in terms of its intensity distribution. So this is another example of if you happen to have field measurement set, which fills this UV plane spatial frequency domain in this fashion, you will get a reasonably good point spread function, which is has a very tall peak here, but has finite amount of artifacts around, which you need to account for. You cannot imagine, you cannot infer that this is a new source that you have found in the field, even if there was only one point source. You might see these additional responses which have to be attributed to this, and only after doing that you can see whether there is any another source. or another intensity feature. So these are just examples of, this is a dirty image of the Jupiter at L-band, and this is the clean image of Jupiter. Now you'll see it's this, at least in the case of Jupiter, you know that, it doesn't have replicas like this around. In the field that you might have chosen, there may not have been any other sources. But you see these replicas because of inadequacy of sampling. But once you account for them properly, you will see a genuine description of the intensity distribution. So as I said, each one of the baselines is capable of measuring over the 6 hours a track, measurements along a track, which are typically along an ellipse. In general, the line being a spatial case of an ellipse and circle being the other extreme case of an ellipse. So our idea is to make use large number of felt pens and draw tracks with them. We are allowed to. We can also use thicker felt pens to fill this. And what is a thicker felt pen will amount to? Remember that each one of these tracks is at a distance, the lengths, the distances from the center are measured in units of physical distance divided by the wavelength. Now, when we are using a finite bandwidth, we are looking at different wavelengths, no matter how small separation they might have. And you will find that the same physical separation will amount to different spatial frequencies corresponding to different frequencies, the temporal frequencies. Because the lambda is different, the same physical length d will amount to slightly different d by lambda at different lambdas. And so that, that can be used to gain certain thickness for the felt pen that we're going to use to draw these tracks. When that aspect is used, it's called bandwidth synthesis. The aperture synthesis is benefiting from using large number of baselines, large number of antennas, which allow us to make NC2 pairs. Each pair can measure a particular point in this plane. With Earth rotation, we can use the same pair to measure information along a track in the UV plane. That's called Earth rotation synthesis. And in addition to that, we can use the dimension of finite bandwidth, where we use information at different wavelengths, closely spaced, which allow us to, at a given point, measure information along the radial direction. Different points will be measured across the bandwidth. So it's like using a thicker felt pen. So when all these three things are put together, you have done aperture synthesis using Earth rotation and the dimension available along the spectral width, which is called bandwidth synthesis. So you can benefit from all this and make as many. So I think, oh, I'm going back. I'm so sorry. All right, you can get, near, complete coverage for certain directions and synthesize as big as the 25-kilometer aperture using the information in the Fourier domain, and then have a point spread function, which is as if you have a circular dish, in which case you will see a airy pattern like this. So of course you can keep the information. Sometimes you would like to study the spectral dimension explicitly, because there might be a spectral line. Intensity may not be constant or roughly constant across the frequency in the band that you're looking at. So essentially, you might land up creating pieces of information, which is either in terms of visibilities that you measure similarity of the signal between every pair of antennas, and that information compiled in the plane of special frequency domain. So you can measure visibilities as a function of time and frequency and polarization, and keep that information intact in the spatial frequency domain, but keep the frequencies separately, or Fourier transform them, make the images, deconvolve them, and still keep the spectral domain intact, in which case what you get is a information cube, which has two directional coordinates and a spectral dimension as well as the third dimension. So people have been using this technique routinely, and we have seen great progress in this. This is the state of art at the present time. You have the resolution, very high resolution now achievable at range of frequencies covered by various telescopes, which are shown here. You will find the resolution here is in arc seconds, and the lower the number, better it is. And so you can see that such fine resolutions are obtainable with very long baseline arrays and interferometers, which also has with elements which are launched in space, the space interferometers. So you can get to, these are large number of examples of such. I'm not going to go into details. These are easy to find on the web. These are beautiful images made using such telescopes, which show fascinating details. This is one of the famous sources, Cassiopeia A. This is a supernova remnant of, it's a historical supernova remnant. This is the Jupiter magnetosphere. This is one of the accreting neutron star, SS433, famous source. This is center of our galaxy viewed with the VLA using various configurations and combining the data together, which shows fascinating details, which are so you know that VLBI is also routinely used these days, where you can synthesize a Earth-size aperture and get resolutions corresponding to what you would get if you had a telescope of that size, going down to milliarc seconds routinely. All of you must have been seen this news in the recent time using the Event Horizon Telescope, which imaged the black hole at the center of M87. So it was possible due to this technique. You can also see how using different telescopes, you can study scales, details of the source on different scales, and using different frequencies with the same instrument, how you can refine your ability to see the details with the clarity. And you can see the hierarchical zooming here, showing fascinating details at the level at which you would not have imagined with normal equipment. So the quest for bigger and better and more sensitive instruments to probe deeper continues. Multi-wavelength nature of probe is now more implicit. Earlier, people used to say, I'm a millimeter wave astronomer, I'm a decameter wave astronomer, because they had instruments which were, focused on those frequency ranges, and they were largely busy, collecting some information now. But after having information about sources at various frequencies, to understand a particular object, you require the entire jigsaw puzzle together, all the pieces together in the jigsaw puzzle to understand the mysteries about these sources. So it has become a multi-wavelength pursuit, and it has now even been extended to multi-messenger pursuit. So you are all aware of the square kilometer array, which in your times will be a fun toy for you guys to play with. Of course, in doing all this, you have to be aware of contaminants and the signals that do not come from the sky but spoil the fun while looking at.
We probably need to round up, because it's about 1:15 now. So
Okay, so I'm stopping here right now.
Yeah.
I'm really at the end. So you have to be watchful of these, and your generation can take care of making sure that you get sky signals without much contamination by reducing the dependence on use of bandwidth for other communication purposes and so on and so forth. So this is where I will leave you. Thank you for listening. I think we have lost many.
we have lost many, and the time for the next session is not too far away.
Yeah.
So maybe we can take questions later,
Yeah, I think we can take questions later.
and we'll get together again at 2:00.
All right.
Yeah.
So I will join at 2. Yeah.
Okay. Thanks a lot, Desh.
Thanks.
Thanks very much. Thanks.